To another movement learning session where I'm working with oh, there's a little bit of echo there. That's definitely not right. Hi, another movement learning session where I'm continuing to work through the Feynman Lectures in physics. You can find the website here, feynmanlectures.caltech.edu. And last time we were in the chapter on the theory of gravitation and specifically Cavendish experiment. Yeah, which is a simple experimental approach that lets people measure the gravitational constant directly. So yeah, continuing working through these notes, trying to attend to myself well, and interacting with people today through YouTube. Started channeling this to YouTube and still watching the Twitch feed also on Vaughn.live, Vaughn TV, um, all kinds of outlets where you can ask a question or interact with me a little bit. Not like I am an expert on the subject matter, but maybe you might be interested in any specific detail about how I'm organizing myself here. So yeah, there's the apparatus anyway for the Cavendish experiment, and so this rod is dangling, and it's made symmetrically, and the whole apparatus is set up symmetrically with two masses set up that are identical to each other, and they're in equal distance in opposite directions. And so the presence of these masses is going to introduce a twist into this wire. And so by measuring how much the fiber gets twisted, I guess that detail remains to be clarified. You can measure the strength of the force and then plug it into this expression for gravity right there. Yeah, I'm not completely clear what are the two masses in that equation, because it's this little mass being attracted to that thing. Right, maybe, yeah, it's some kind of difference experiment. So is it like it's this mass in both cases? Yeah. It says large and smaller balls of lead. Hmm. So yeah, that's Cavendish experiment. I kind of feel like finding one of those movies because I've seen really simple setups This is pretty simple looking. This is actually bowling balls. Huh. Okay, so now the time lapse is going. As you can see, there's a little bit of drift left over. Because, of course, okay, this is great. So, not the air currents, I guess. I mean, when he walked in there and put the balls down, there is a chance it disturbed it that way. Hmm. All right, I could be more convinced. Oh, it's still going. Yeah. I've seen some like do-it-yourself grade versions of it. They're similar to that. It's like an ad. Okay, I don't know what to say. That demonstrates it. Probably the other ones do the math better. Because yeah, there must be something about the symmetry of the setup that makes it easy to plug into this equation. But I'm not gonna get bogged down in it. Anyway, but what is gravity? Blah blah blah. It's a question that bothered me as a young person. I guess it still bothers me a little bit. Many mechanisms have been suggested. So there was an idea that there's some kind of background source of particles streaming into the Earth that imparted the movement. And the sun screened the particles. So that makes a net push towards the sun. What is wrong with that machinery? It involves some new consequences which are not true. The Earth, in moving around the sun, would impinge on more particles which are coming from its forward side than from its hind side. Therefore, there would be more impulse given to the Earth from the front. The Earth would feel a resistance to motion and would be slowing up in its orbit. So we'd slow down. And so that's not a good prediction. All the other force laws give the wrong predictions, says Feynman. No machinery, or no, that's not what Feynman says. No machinery has ever been invented that explains without also predicting something which doesn't exist. There you go. That's exactly what Feynman says. So, yeah, why is gravity so weak? Gravity over electricity is a tiny, tiny number. That's specifically the repulsion of two electrons and the attraction due to their masses. 4.17 times 10 to the 42. That's, yeah, amazing. Where could such a tremendous number come from? Some say that we shall one day find the universal equation, and in it, one of the roots will be this number. It is very difficult to find an equation for which such a fantastic number is a natural root. Other possibilities have been thought of. One is related to the age of the universe. Clearly, we need to find another large number somewhere. But do we mean the age of the universe in years? No, because years are not natural. They were devised by men, by people. As an example of something natural, let us consider the time it takes light to go across a proton, 10 to the negative 24 seconds. If we compare it this time with the age of the universe in years, the answer is 10 to the negative 42. So it's been proposed that the gravitational constant is related to the age of the universe. If that were the case, the gravitational constant would change with time, because as the universe got older, the ratio of the age of the universe to the time which it takes light to go across a proton would be gradually increasing. Is it possible that the gravitational constant is changing with time? All right. Yeah, I never read this part carefully enough. And yeah, so that's some deep theoretical physics. Something natural is the time it takes light to go across a proton. Hmm. That's less good movement organizing. When the liquid goes down the wrong hatch. One test which we can think of is to determine what would have been the effect of the change during the past billion years, which is approximately the age from the earliest life on the Earth to now, and 1/10 of the age of the universe. In this time, the gravity constant would have increased by about 10%. It turns out that if we consider the structure of the Sun, the balance between the weight of its material and the weight at which radiant energy is generated inside it, we can deduce that if the gravity was 10% stronger, the sun would be much more than 10% brighter, by the 6th power of the gravity constant. If we calculate what happens to the orbit of the Earth was then closer in. Altogether, the Earth would have been about 100 degrees Celsius hotter, and all of the water would have not have been in the sea, but vapor in the air, so life would not have started in the sea. So we do not now believe that the gravity constant is changing with the age of the universe. Such arguments as the one we have just given are not very convincing, and the subject is not completely closed. I find that to be a compelling argument. It is a fact that the force of gravitation is proportional to the mass, the quantity which is a fundamental measure of inertia. How hard it is to hold something which is going around in a circle. Therefore, two objects, one heavy and one light, going around a larger object in the same circle at the same speed because of gravity, will stay together because to go in a circle requires a force which is stronger for a bigger mass. That is, the gravity is stronger for a given mass in just the right proportion that the two objects will go around together. If one object were inside the other, it would stay inside. It is a perfect balance. Therefore, Garrigan or Titov would find things weightless in a spaceship. If they happen to let go of a piece of chalk, for example, it would go around the Earth in exactly the same way as the whole spaceship. And so it would appear to remain suspended before them in space. Masses and weights are exactly proportional within 1 part in a billion or less by experiment, done first by Eötvös in 1909, and more recently by Dickey. That's cool. Confirming that. And then famous relativity. Right. Newton thought gravity was instantaneous. And Einstein argued that you couldn't communicate faster than the speed of light, so gravitation was wrong. And an easy feature to understand is that anything which has energy as mass in the sense that it is attracted gravitationally, even light which has an energy has a mass, in quotes. But it doesn't have mass. But when a light beam which has energy in it comes past the sun, there is an attraction on it by the sun. It gets deflected by the sun. Yeah, and notice that Feynman's choosing to express it that way and not in terms of space-time being bent itself. It's a popular formulation, I guess. But yeah, maybe over emphasized from other things I've read, like Victor Toth on Quora. Finally, let us compare gravitation with other theories. And there is no quantum gravity, as he explains. Proof is not given in the course. What is? All right, that's the chapter on gravitation. The first chapter talking about gravitation. Probably still going to talk about it for a bit. So, lecture 8, motion itself. The basic, you can see on the blackboard the basic calculus definitions. The relationship between distance, velocity, and acceleration. Even has a definition of a limit, the definition of the derivative. Sorry, not the definition of a limit. Definition of the derivative doesn't really define the integral, and describes a component notation for velocity in 3 dimensions, Cartesian basis. Okie dokes. That's what the graphic looks like. Description of motion. The simplest change to observe in a body is the apparent change in its position with time, which we call motion. What a nice statement. Not a convenient way to do that. There you go. Ooh, this is a little sexist. Change of a woman's mind. More difficult types of movement to describe. Perhaps even the changes in the mind may have a parallel in changes of the atoms inside the brain, but we have no such knowledge yet. Oh, the humility. At any rate, that is why we begin with the motion of points. Think of them perhaps as atoms or small objects. Small compared to the distance moved. Hmm. Right, when you're describing the movement of the car, you don't distinguish the parts of the car. You just pick a landmark. I think I have read this chapter before, kind of carefully. So we're describing the movement of a car. And there we have a table. So as the minutes advance, the distance increases in this way. So between minutes 4 and 5, right, the distance hardly changes. So yeah, looks like that when you plot it. And yeah, like the table had discrete points. This is an interesting thing already. The table has discrete points, so those are the plotted things, and then they're connected with a smooth line. For a complete description, one would have to know where the car is at the half-minute marks too, but we suppose that the graph means something, that the car has some position at all the intermediate times. Different type of movement, so that's for a falling body. So as the time increases, the distance is increasing with the square. You fit that curve. Okay, right. And then if you wanted to think about a similar thing for the movement of the car, this complicated plot, you just call it a function of time. In this case, I guess it's a function. What do we mean by time and space? Theory of relativity shows that our ideas of time and space are not as simple as one might think at first sight. However, for our present purposes, for the accuracy that we need at first, we need not be very careful about defining things precisely. Perhaps you say, that's a terrible thing. I learned that in science we have to define everything precisely. We can't define anything precisely. If we attempt to, we get into that paralysis of thought that comes to philosophers who sit opposite to each other, one saying to the other, you don't know what you are talking about. The second one says, what do you mean by no? What do you mean by talking? What do you mean by you? And so on. In order to be able to talk constructively, we just have to agree that we are talking about roughly the same thing. You know as much about time as we need for the present. But remember that there are some subtleties that have to be discussed. We shall discuss them later. Another subtlety involved and already mentioned is that it should be possible to imagine that the moving point we are observing is always located somewhere, whether or not we're looking at it. It turns out in the motion of atoms, this idea is also false. We cannot find a marker on an atom and watch it move. That subtlety we'll have to get around in quantum mechanics, but the first thing to learn what the problems are before introducing the complications, and then we will be in a better position to make corrections and lay the more recent knowledge of the subject. We shall therefore take a simple point of view about space and time. That's the Newtonian or classical perspective. So speed. So Feynman says that the Greeks, Arabs, and Babylonians didn't have geometry or algebra to properly deal with motion or easily deal with motion. So try solving this problem by sheer algebra. A balloon is being inflated so that the volume of the balloon is increasing at a rate of 100 centimeters cubed per second. At what speed is the radius increasing when the volume is 1,000 centimeters cubed? The Greeks were somewhat confused by such problems, being helped, of course, by some very confusing Greeks. Goes through Zeno's paradox. This is a subtle paragraph, but um, if you are a positivist and you think that measurement is the only definition of anything, then that's what the speedometer says is the speed on the car. But a person objects, my speedometer is broken. So does that mean the car isn't actually moving? No, the velocity has a meaning independent of the speedometer. And that's why the speedometer isn't working right or the speedometer is broken. That's why it means something. Yeah. So yeah, making a case for needing to be more precise about velocity. And so getting at the instantaneous velocity idea, what the speedometer says is its instantaneous velocity. In a short time, epsilon, the car or other body goes a short distance x. So its velocity over that interval is x over epsilon. As epsilon is smaller and smaller, this approximation approaches its instantaneous velocity. Right. So yeah, that's a limit. Can't do that with the lady in the car because the table is incomplete. All right, so this next section I think is the kind of thing that I didn't work through carefully enough the first time I did this. I'm gonna try to digest this properly. So we know where the ball. I guess I should. Oh, great! I can just mouse over it. So in second 5, okay. So at second 0, it's at 0. Second 5, it's at 400. So time is equal to 5 seconds. Displacement is equal to 400 feet. All right. Yeah. So this is the technique. At 5.1 seconds, the distance is gone altogether because we know the formula for its movement. In feet. This is yeah. Empirical formula. So then Oops. Yeah, zoom out. Yeah, so then the delta S is 16.16 feet for delta T is 0.1 seconds. Oh yeah, of course. I see. So yeah, 16.16 over 0.1, 161.6. So feet per second. So that's the velocity over that interval, but it's still, if you want to know the velocity exactly at 5 seconds, Feynman's saying, you can work with an even smaller infinitesimal. Right. So if you work with a thousandth of a second, okay, so to perform the mathematics, we state the problem a little more abstractly. To find the velocity at a special time, which was the original, wait, we were interested at 5 seconds. We know the distance at that point. To find the velocity at those points, we need to no, I don't follow this. At the time t naught plus a little bit, where is the body position at 60? Oh, okay. Yeah, just expand it out. Okay, I can see that now. Okay, that's cool. Yeah, okay. So the position is 16 times the time in seconds squared. So if we want the velocity we can add a little bit to that distance. T plus some tiny amount of time in the future squared. Expand that out. That's 16 t squared plus 32 t epsilon plus 16 epsilon squared. So this is the, and then this is going to be like S prime. These are all T naughts. So it's altered position. Okay, yeah, it's altered position. Includes the original term. Then here's the change. So Alright, I shy away from this, but I may as well. Do it live. Do it live. Alright. So, I'm saying, let us say, that the position of something is this more complicated function, coefficient a t cubed plus some other coefficient b times t plus c, constant, describes the movement on a point. And so we're interested in considering an increment. After that increment, the position is changed, and the increment is t plus delta t, which is now cubed, plus b times t plus delta t plus c. And it looks like, set out further, yeah, so t plus delta t cubed, what is that? A times, so it's t times, oh yeah, I guess I can write it out this way. Yeah, this is going to be something times itself times itself plus dot dot dot. So t cubed, t times t times t, and t times delta t times t. t times delta t again. Sneak a 2 in front of that. And then delta t times t times t. So that's another t delta t. Delta t times t times delta t. There's probably more than one of those. Delta t squared. Wow. Already getting tedious. So let's use some other notation. A plus b, a plus b, a plus b. So that's a times a times a is a cubed plus a times b a times b times b. So this one's been, is that all the options? Yeah, there's 3. No, that's not right. This one times this times a times a. This one times a times b. This one times b times b. Oh, but there's 2 ways of doing each of those. I must be rushing or something. A squared plus 2ab plus b squared. Hey, look, I did one of them. Times a times a. Let's just do that. So distribute the a. So yeah, okay. A cubed plus 2a squared b plus b squared a plus dot dot dot. Then a squared b plus 2ab squared plus b cubed. Okay, so then I have to group those. It's equal to, okay, I'm doing it now. A cubed, so a squared b's, there's 3 of them. And there's 3 ab squareds. And a b cubed. Okay, I think that's right. So then, so this line is a times t squared, sorry, t cubed plus 3t squared delta t plus 3t delta t squared plus delta t cubed, right? That still need a dot 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 after that. Okay. And what to do about it's like I wanted to lose the previous layer, but I'm not ready yet. Okay, that's what I'll do. Oh, this isn't going too well. What's the problem here? I want this. Here. All right, that actually works fine. So it's took the wrong stuff. Okay. It's gonna happen. It's gonna happen, people. They look like I'm having fun. Sweating a bit. Copy that. Go over here. Keep it. All right. So those are the A terms. Oh, it's good to practice this stuff. S plus delta S. So that's AT cubed plus A, oops, looks like a delta. A. Do 3 AT squared delta T plus 3 AT delta T squared plus A delta T cubed plus dot 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 dot. Now you finally get that B term. That's a little easier. B T plus B delta T plus C. Okay, those are all the things, I guess. And then so if we want to just get the delta S, we have to subtract now the S from the original thing. So S plus delta S minus S is equal to all that minus the things above. So I'll just start putting it together. So AT cubed minus AT cubed plus this term stays 3AT cubed delta T plus, ooh, getting uncomfortable here, 3AT delta T squared dot 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 A delta T cubed plus B times T minus B times T plus C minus C. Oh, and then I almost lost my plus B delta T. Is still there. And so then that simplifies it quite a bit. And we have 3 AT cubed delta T plus 3 AT delta T squared. Sorry, that should be T squared delta T. T squared delta T. Those ones stay. And the A delta T cubed stays. That one didn't cancel either. Or did the B delta T? 1, 2, 3, so 4 terms left. 3a t squared delta t plus b delta t plus 3a t delta t squared plus a delta. Good. Yeah. So I get this, but we do not want delta s. We want delta s divided by delta t. Then delta s over delta t is equal to all that divided by delta t. So I'm just going to cancel them as I see them. So 3a t squared delta t is canceled plus 3a t 1 delta t now plus a delta t squared plus b. So delta t's left. Yep. And then as delta t goes to the limit of 0, right. So the limit delta t approaches 0. Wow. Okay, yeah, so you can just plow through it. That's the hard way. Or you could just use 3a t. Yeah, or you can use your, what do you call that? That rule in calculus? Power law? So rules about derivatives, power law, product rule, composition, and the chain rule. The last one's the chain rule. I always forget the chain rule. Hello out there. I'm just going to take a short break. Can be reminiscing on integrals if you want in the chat. Okay, continuing with Feynman Lectures on motion. Turns out it's an introduction to calculus. So the inverse problem, got a series of speeds for different times. We're interested in getting the distance. This is the sort of painful thing. Each function can be differentiated analytically. The process can be carried out algebraically. It leads to a definite function. It is not possible in a simple manner to write an analytical value for any integral. You can calculate it, for instance, by doing the above sum, right, by approximating it. Acceleration, the change of velocity then. So in this previous problem, we just did by brute force that the velocity at a particular time is 3at squared plus b for that expression of its position. Since acceleration is the derivative of the velocity with respect to the time, we need to differentiate the last expression above. The body starts from rest and moves with a constant acceleration g. Its velocity at any time is given by. Right. The distance is the integral of that. This way of writing the second derivative. Okay, so then he gets into components. Okay, so then some projectile motion type stuff. So the ball is going to move horizontally with a constant velocity u, and then it's accelerated downward. What is the motion? So you can say that the change in the x position with respect to time is the velocity in the x position, and that's what we're calling u, right? Since it's constant, the x position is its x velocity times time. And since downward acceleration is constant, the distance goes by that integral. What is the curve of the path, the relationship between y and x? We can eliminate t from that second equation, since of the first equation, x over u is t. So we put that substitution in. The y change is negative g over the x velocity squared. Interesting. Negative parabolic movement. Okie dokes. Well, that concludes the motion chapter. Chapter 8. Still doing quite a bit of classical physics, Newtonian physics. This is going to be more on momentum and inertia, maybe clarifying some of the earlier points. Yeah, but it is a relief to know that weight and mass have been shown to correlate to better than 1 part in a billion. So thank you, scientists, for being careful about that. And yeah, tomorrow is the movement organizing live stream, where I work with material that is perhaps more directly interesting to somatic educators, less about me organizing my soma and more about how that fits into the big picture. So yeah, see you in this time slot tomorrow. And if you want to continue with the Feynman lectures with me, then next week, next Wednesday, will be the time where I'm picking that up. Otherwise, you can find me at SOMATI.CA. Class times are listed there, and my contact information is there if you're interested in anything else that's going on. Have a good one.